Okay. Let us post there. Let us post the video there so that we start the discussion. I'm seeing people have joined. So we start. It was an introduction on illumination. Today we only have one thing that we want to discuss, is the laws of illumination. You realize that your syllabus in this unit is very small. So I will not rush you up with things. So we will be taking steps by steps in doing these things. So today we'll only cover the laws of illumination. And you remember last week, we did the introduction of illumination. We did the introduction, the concept, the terms used. And we also did introduction to things like the types of fixtures, how we do the fixtures, which one is for which room, how do they look like. So I want us to start this discussion today, and I would like you to mute your mics if you don't have any question, or if you have a question from the previous class, we can answer the questions before we get into the laws of illumination. So I'll give room like for 2 minutes for asking questions, so that any coming up issue from the previous class we can discuss before we go to we start today's topic. So anybody with a question? Kasheru?
Yes.
Any question?
No.
You are okay. Salad?
Yes.
Yes.
You're very okay.
I have a question.
Yes.
It's not this class, but for the home class,
Mm.
you have not put procurement
Notes.
note. Yeah.
Gasheru called me, and I think you also wrote an email to me.
Yes. Yes.
And I told Gasheru that even the Friday notes, I've not posted them. But when I'll be posting them,
Yes.
I'll post the procurement notes.
Okay.
Is that okay? I'll post them on Friday. The procurement and the ones that we learn on Friday. Any other question? I want questions from the previous class for this unit. Questions on illumination, things that came up that you guys realized. And by the way, is this the class that I gave you assignments to do, Salad, or it is EMFD? Hassan,
Yes. Yes.
is this the same class that I gave you assignment?
EMFD ile ya kusubmit ya discussion.
Sio ya kusubmit, kuna ile yenye niliwaambia mtafute past papers question.
Oh.
Ilikuwa ni gani? Ilikuwa ni workshop ama ilikuwa ni nini?
Niangalie, kuna mahali niliandikanga.
Hivyo hata hamjafanya.
Unajua tulisema tunakuja ku represent, kila mtu amechukua subtopic alafu tuna represent.
Mlikuwa mnaleta questions, kila mtu alikuwa atafute hizo questions za hizo topic, alafu mnaleta hizo questions tuna discuss. See, that is what I said. Which unit was that?
EMFD.
Oh, EMFD. EMFD ni kesho tu, si ni kesho?
Tulisema endega
ni kesho ama ni leo?
Leo jioni.
Oh. Ni leo from saa 8?
Ni leo jioni. Tulisema endega ni first topic ya maintenance, corrective maintenance, preventive.
Wasomee wasikie so that ikifika hiyo time msiniambie mwalimu hatukujua.
Alafu Humphrey tulisema safety prescription of maintenance. Alafu tukasema Gacheru common fault on DC machine. Tukasema Peter functional test after repairment of a machine. Na tukasema Hassan safety prescription of a DC machine.
Sasa hizo mtafanya tukifika saa 8. Hiyo ndio kazi tunafanya kwanza before tusome kenye tunafaa kusoma hiyo time. Si hapo ni sawa?
Humphrey, si umesikia yako? Humphrey ameingia saa hii.
Humphrey, mwambie yake.
Humphrey yako ni safety prescription of maintenance. Umesikia?
Sawa. Aya, tuendelee sasa. You mute your mics kama hamna maswali tena. If you don't have questions, let us mute our mics. Then start now. Illumination, as we talked about it last week, we said illumination is the way of lighting. It is lighting a room or making a room to have some sunlight so that you can see the objects or the occupants of the room, or you can work on something inside the room. So today I want us to discuss on the laws of illumination. That is the only thing we are discussing today. So I want us to be very careful because it is a very important concept in illumination. It is a calculation. I tried to avoid it because it has a lot of calculations so that we can do them when we are in the university. But I cannot avoid it anymore because we have to do it before we go to the next topic. So I would like you guys to be very careful and look at what we are doing so that you ask questions where you don't understand. So we start with the introduction. We say that light is the prime factor in the human life as well as activities of human beings ultimately depend upon the light. Now, where there is no natural light, use of artificial light is made. And that is now when we come up with the illumination part. The artificial lighting produced electrically on account of its cleanliness, ease of control, reliability, steady output, as well as its playing an increasingly important part in the modern life. So the science of illumination engineering is therefore becoming a major importance. So illumination is a very important aspect because where we cannot get the natural light, the natural light is sunlight. So at a situation where we cannot get the natural light, so we have the artificial light. And artificial light obviously is what that is caused by electricity. Either whether DC light like torches that are powered by batteries, or those that are powered by AC current. That is, Moses, you mute your mic. Okay, I've already muted him. I hope you are listening. Even if I've muted you, you can still hear me. Natural light, the light in a form of radiant energy. Natural light is a light in form of irradiant energy. So various forms of incandescent bodies are the sources of light, and the light emitted by such bodies depend upon the temperature of the bodies. So heat energy is radiated into the medium by a body which is hotter than the medium surrounding it. So the heat of the body is seen, can be classified as red hot or white hot. So hot body becomes 500 to 800 degrees Celsius and becomes red hot, and above 2500 and 3000 degrees Celsius, the body becomes white hot. So the body is white hot when it has very high temperature of 2500 300 degrees centigrade. So when the body is red hot, the wavelength of radiant energy will be sufficiently large and energy available in the form of heat. Further, the temperature increases. The body changes from red hot to white hot state. So the wavelength of the radiant energy becomes smaller, and the range of the wavelength of light. So the wavelength of light waves vary from 0.004 to 0.005 millimeters, i.e., that is 4,000 to 7,500. Now, relative sensitivity. We need to know some of these concepts, because when we will go to the calculations, you will only be needed to recall what we had defined. So relative sensitivity, the reacting power of a human eye on the light waves of different wavelengths varies from person to person and also varies with age. So the average relative sensitivity is shown in this figure. The sensitivity of the eye on yellow-green radiation is taken as a unity, or 100% of the sensitivity to other wavelengths is expressed as a factor of percentage. So the relative sensitivity at a wavelength is written as K lambda. This is called lambda, known as the relative intensity factor, normally called lambda. Those guys who took physics in high school, you know that. So the wavelength of rays, you can now see how they vary. I can zoom out so that you see. So the color, the sensation of the color is due to the difference in the wavelength of light radiations. And now we have visible light can have a wavelength of a light between 400 to 7,500, as shown in the figure. Now we can see X-ray rays, gamma rays, ultraviolet rays. Between this age and this age, the visibility is very high. Microwave, infrared rays, the FM, the AM, that is the radio frequencies, and the long radio waves. So you can see the rays. And the range of visibility is between the gamma rays and the microwaves. So they show the light. You can be able to see them. So now we have the wavelength on the color of the color light. So the violet has the wavelength of 4,000. It increases. Green goes to 5,000. Yellow, orange, and red, and then infrared. So illumination. We now go, want to start the calculations of illuminations. Now, illumination differs from light very much, though generally these terms are used more or less synonymously. Strictly speaking, light is the cause of illumination, is the result of the light on the surface on which it falls. Thus, illumination makes the surface look more or less bright with certain color, and it is this brightness and color that the eye sees and interprets as something useful or pleasant. So it is this color. So illumination is just what makes the surface to look more bright. So that what makes the surface look bright, it is what the eye sees. So it is what you look at and say that I've seen a certain color or I've seen a certain object. So that is called illumination. The light may be produced by passing an electric current through the filaments as in cathode lamps, through arcs between carbon and metal rods, and through suitable glasses as in neon and other gas tubes. In some forms, the lamps, let me zoom it out so that you guys can see. In some forms of lamp, the light is due to the fluorescent excited by the radiation arising from the passing electric current through the mercury vapor. So some bodies reflect light in some measure, and others illuminated from the original source. They become secondary source of light. So the good example is the moon, which illuminates Earth by means of reflected light originated from the sun. So the moon illuminates by reflection. So we have different types of light transmission. We have reflection and refraction. The terms used in illumination, we have the plane angle. The angle subtended to a point plane by two conveying straight lines, and its magnitude is shown by theta. That is the length of the arc of the radius. It is measured in radians, and the largest angle subtended at a point is 2n radians. So radians is the angle subtended at a point by an arc whose length is equal to the radius. You can see how that is explained. That is the plane angle. Then we go next is the solid angle. What is a solid angle? A solid angle is subtended at a point in space of an area, and its angle enclosed in the volume formed by an infinite number of lines lying on the surface of the volume and meeting at the point in it is represented by Greek letter omega. So, and it is measured in steradian. So the solid angle omega is equals to area over the radius squared, steradian. So the largest sorry. Let's proceed. The largest solid angle subtended at the center of the sphere, that is area of the sphere, is equals to area of the sphere over the radius. So the area of the sphere is normally known as 4 pi r squared. These concepts are very important. You better get them clearly, because when we will go to calculate the laws of illumination, we will be remembering what we have learned, that there is an angle sphere. There's a solid angle. So the formula for finding the solid angle is 4 pi r squared over r squared. We said the formula is omega, which is equal to the area over, that is the area of that sphere over the radius squared, which is 4 pi r squared over the radius squared. So when we cancel the r squared, we remain with 4 pi steradian. Now, the light is defined as the radiant energy from a hot body which produces a visual sensation upon the human eye. It is usually denoted by Q, expressed in lumen hours, and in analogous as watt hours. So light is measured or denoted as lumen hours or watt hours. So what is the power? So luminous flux F is defined as the total quantity of light energy emitted per second from a luminous body. It is defined as the total quantity of light energy emitted per second from a luminous body. It is represented by the symbol F and is measured in lumens. You can see F is Q over T, which is the total quantity of light energy emitted per second. Per second, that is per. When we say per, it means we are dividing. So per second, it means it is the luminous flux F is equals to Q, which is the quantity of the light energy over T times seconds. The next definition is the light intensity I. It is the luminous flux per unit solid angle in the given direction. It is represented by I and is measured in lumen per stadia, or candela. Sorry. So luminous intensity is measured in candela, which is equal to I is F over omega. We know F of omega, F over omega. So F over omega, we can insert these equations and get that because we already said omega is equals to area over that. And we can replace 4 pi r squared over pi r squared divided by q, and we'll get that. So lumen, what is lumen? Luminous flux emitted by a source of 1 candela power in a unit solid angle. So lumen is equals to candela power of source times the solid angles. That is the candela power, that is the Cp times omega. So the candela power, which is the Cp, is the candle power of source that is defined in a number of lumens emitted that the source in a unit solid in a given direction. Illumination E. Illumination of a surface defined as the luminous flux received by surface per unit area. It is represented by the symbol E and is measured in lux, that is lumen per meter squared. This is a very important formula. Illumination E is known as lumen per meter squared. That is the illumination of a surface defined as the luminous flux received by the surface per unit area. Light is the light is the cause the illumination and its effect. So the brightness and luminance is defined as the luminous intensity per unit projected area of the given surface or a given direction. So the brightness or luminance, we had already said in the last lesson last week that brightness is also called luminance, and it is defined, it's got by illumination, that is I, and we said illumination, that is luminous intensity I over the area, the projected area. So it is normally candela, and we said the luminous intensity is represented as candela. So it is luminous intensity I over area, which is A, which is the luminous intensity candela over meter squared. That is the area. Area is normally meter squared because a distance, a meter squared means that it's the distance times distance to make it squared. So we are still on the definition. The main horizontal candela power is defined as the mean of the candela power in all the directions in the horizontal plane containing the source of light. So the mean spherical candela power is defined as the mean of the candela power in all the directions and in all planes from the source of light. So the mean the mean hemispherical power candela is defined as the mean of the candela power in all directions above or below horizontal plane passing through the source of light. Reduction factor of the source of light is the ratio of its mean spherical candela power to its mean horizontal candela power. So you can see the calculations there. And then we have the lamp efficiency. It is defined as the ratio of the luminous flux to the power input. Luminous flux, we say it is the output. So it is the output over the input. It is expressed in lumens per watt. So the input, it comes in as power, that is input power, over the output. The output, we said, is lumens. And you remember in our other slide that we said what is defined as lumens is the luminous flux, the quantity of the total quantity of light energy emitted per second. That is the lumens. Then we have the space height ratio. It is the ratio of horizontal distance between the lamps and the height of their mountings. Sterilization factor or coefficient factor, that is UF, is the ratio of the total lumens reaching the working plane and the total lumens given by the lamp. Maintenance factor MF is the ratio of illumination under normal working condition to the illumination under clear and clean conditions. Depreciation factor DF is the ratio of the initial illumination to the maintained illumination and the working plane. So glare, we had already talked about glare. Glare is the brightness within the field of vision such that a character as a cause of annoyance and or discomfort, interference with the vision of the eye. We said glare is too much light, and the light or brightness, too much brightness that can spoil the eye. So this is found in a car headlights. Relationship between omega and single angle, that is the single solid angle, that is the surface area of XYZ over the radius squared. We have talked about that. So those are the calculations there. So I want us now to go straight to laws of illumination. So we are done with the definitions. So right now we are just now going to use whatever we have defined in explaining the laws of illumination. And I want us to follow them closely because they are also very important laws. So there are two major laws of illumination, that is the law of inverse square and the Lambert's cosine law. So we start with the law of inverse square, or the inverse square law, normally known as the inverse square law. The inverse square law, what it says is, this states that the illumination of a surface is inversely proportional to the square of the distance between the surface and the point of source. I repeat, the inverse square law states that the illumination of a surface is inversely proportional to the square. It is inversely proportional to the square of the distance between the surface and the point of source. So the proof, in proving, we are just defining, we are trying to solve or show that formula. So proof, let S be a point of source of the luminous intensity. We can see the point S from that diagram. And then between the surface, let me zoom this out for you guys to see. And then I is the candela, that is the luminous flux emitting from the source. A1, A2, and A3 are the three parallel surface areas of the square in square meters. And D, 2D, and 3D, the distances A1, A2, and A3 from the point source, respectively, as shown in the figure. So for the area A1, solid angle omega, that is A1 over D squared. So flux on area A1, luminous intensity, times the solid angle. So to get the flux area, that is A1, is equals to luminous intensity. We are going to get the luminous intensity times the solid angle. And we say the luminous intensity is represented by I, and the solid angle is represented by omega. So we are going to have I, and omega, we say it is the area of the distance squared, or the m squared. So the area of the distance squared is the A1 over the flux. So we are dealing with the first square. You can see the omega, the distance omega. I'm zooming out so that you guys can see. So the first distance is there. The 2D is there, and the 3D is there. So we are using the omega and the first area there to get to calculate the formula. So the flux on area A1 is equals to the luminous intensity times the solid angle. So you can see it there. So when we bring this together, we're going to get that A1 over D squared, that is equation 1. That is the luminous intensity times the solid angle. And then when we proceed and we go on, we're going to see that illumination E we had already described illumination, and we said that illumination A on the surface A1 is equals to flux over area. We said that illumination is the flux over area, and which is equals to flux. The flux on an area, we have already found the flux here. The flux of an area, we say this is the illumination intensity times the solid angle. So the flux, the illumination now is the flux over the area. So we are going to we got this as I A1 ID, that is I A1 over D squared, A1 over D squared times the area, 1 over area, meaning we are dividing by the area. So we are going to get E is equals to 1 because we are going to cancel the A's. We have cancelled the A's out. So we are going to remain with E, which is the illumination, is equals to I. And we said I is what? I is the luminous flux. We have said that E is a luminous flux. Now it's going to be luminous flux over the distance squared, and it's measured in lux. So similarly, similarly, illumination E2 on the surface A2 now will be E2 is equals to 1 over 2 ED D squared, simply because the distance is now 2D. Now the distance is squared, we add D squared, now it is 2D squared. And the E3 now, which is the illumination, the third illumination for the third surface, is going to be E3 is going to be I, which is the flux over the 3D squared. All of them are squared. So that is how it moves on. And now we can see that E1 to E2 to E3 to is equals to 1D squared to 1 over 2D squared plus 1 over 3D squared. And it goes on and it goes on. And we have now proved that it states that illumination on a surface, now like a surface like this, surface like this, illumination on a surface is inversely proportional to the square of the distance of a surface E1 or E2 or E3 is inversely proportional to the square of the distance of the source of light. The square of the is inversely proportional. It means that it is over. So when this increases, this one will decrease. That is why we mean by inversely proportional. For example, if E3 if E1 is 4, if E1 is 4, so D will be a half, meaning it is inversely proportional. When this increases, this one will decrease. That is what it means. So I'm done with the inverse square law. And because I don't want to run very fast, because this is the laws are the only thing we are discussing today, I would like to have a break and want to hear from you guys up to the point that we have reached. What have we had and what are the challenges that we can say that we are getting before I go to the next law, which is called the Lambert's consign law. So I want to hear questions from you guys. So unmute your mic so that I can listen to your questions. Unmute your mics. Yes, Gasheru. Yes, say something. Somebody say something.
Madam,
Yes.
shida yangu ukifanya naona ukizoom naona tu pande moja tu ya slide. Sasa usizoom sana.
Oh, but sasa unaona?
Sahii ikiwa hivi naona, lakini ukizoom sana naona tu slide pande moja pekee.
Oh, okay, sawa. Now nataka mcomment on what we have learned. Did you get anything from the inverse square law?
Yes.
Oh, anybody with a question or a challenge? Na watu wanapotea aje? Ni bundles zinawaishia?
Nadhani.
Kwani nyinyi mnatumia gani salad? Mmeanza kutumia zile za 10 GB?
Hiyo si ingawa ametuambia haifanyi.
Mmemuuliza?
Nimemuuliza akaniambia haifanyi.
Oh, nasi nilisikia watu wengine wakisema jana, kuna watoto wanafunzi wa certificate walikuwa wananiambia ati wamesubscribe inafanya.
Sisi hatujui sana. Tujafanya
Nyinyi mmeregister hiyo 10 GB, mmeshaziweka kwa simu?
bado.
Oh, amjatumiwa message na Safaricom?
Bado.
Okay, maybe they are doing it slowly, itawafikia. So that is now inverse square law already tumeshafanya. So imesema nisi zoom out. So let me leave it there and then we go to the Lambert's cosine law. So the Lambert's cosine law, it states that illumination E at any point of a surface. So we can mute our mic so that we listen to this. Now, illumination, it says that illumination E at any point on a surface is directly proportional to the cosine of the angle between illumination E at any point of the surface is directly proportional to the cosine of the angle between the normal at that point and the line of flux. So, I repeat again before we prove. It says that illumination E at any point on a surface is directly proportional to the cosine of the angle. It's directly proportional to the cosine of the angle between the normal at that point and the line of flux. So we are proving that. And you know, in the form of proving, we are just getting formulas. Formulas that we are going to use in calculation when you want to design. When we are going to design, we are going to use this formula. So it is very important for us to see how we are deriving the laws. So discussion. While discussing the Lambert's cosine law, let us assume that the surface is inclined at an angle omega or theta to the line of the flux as shown in the figure. So let PQ, the surface area normal to the source of the inclined, normal to the source and inclined at theta to the vertical axis, and then RS, the surface area of the normal to the vertical axis and inclined at an angle theta to the source angle 0. So we can see here, so this is what we are majorly going to use in our calculations. So that is our theta, the surface area, the normal to the surface is there, and then the surface area of that place or where the light lands, and the lines of flux. So the source, we can see the way it's calculated. Now P, R, Q, S, O, the source is at O. So PQ is equals to RS. You can see PQ is equals to RS. PQ is equals to RS cos theta. PQ is equals to RS cos theta. The illumination of the surface, therefore, illumination of the surface PQ, that is EP, is equals to flux over the area. We normally know that illumination is flux over area, so it is going to be flux over the area of PQ. So which is equals to I omega area of PQ. So which is equal to I over area of PQ times area of PQ times D squared. So when we cancel out this, therefore we get that it is equals to I over D, or flux over D. Therefore, illumination of a surface RS ERS is equals to flux over area of RS, which is equals to flux over area of PQ over cos theta. PQ is equals to RS cos theta, 1 over D squared cos theta. Cos theta is equals to H over D. Now substituting D from the above equation in equation, so therefore ERS is equals to 1 over H cos theta squared times cos theta, which is equals to 1 over H squared cos theta. Those are calculations that you can see there. And then ERS is equals to 1 over D squared cos theta, which is equals to 1 over H squared cos 3 theta. So that is, and now we have already found that we go back to the definition and say that the Lambert square law states that illumination E at a point of the surface is directly proportional to the cosine of the angle between the normal at that point of the line of flux. So the line of flux we said is that is the line of flux. So it is directly proportional of the angle, and you can see that it's directly proportional to the angle at that point. So polar curves, they are the plot drawn between the candle power and the angular position, and the light intensity is not the same in all directions and in most of the lamps because of their unsymmetrical shape. The luminous intensity in all directions can be presented in polar curves. They help to find distribution of candle power, i.e. the light in different directions. So horizontal polar curves, you can see them there. It is the curve drawn showing the distribution of candle power of the horizontal plane about a vertical axis passing through the source of light. So the dip at 90 degrees is due to coiled coil filament occupying the arc subtending the angle. So the vertical polar curves, you can see the vertical polar curves are there. It's the plot drawn showing the relation between the candela power and the angle of the illumination of the vertical plane. So passing through the lamp, the dip at 180 degrees is due to the position of the lamp. So polar curves are used to determine actual illumination of the source surface with the help of these curves. The resonance construction, the vertical plane is in the form of two lobes symmetrical about the vertical axis. So the construction steps: draw circles convenient with the radius of the centers. So this one is not very important in your course, but it's just a definition. But what you are supposed to know, majorly you're supposed to know, is about the laws of illumination and how to get the formulas. Artificial sources of light. So I don't want to go there. Because this is a topic for another day. I'll presenting another slide. So I'm just going to rush over. We have already said this, but I'm just emphasizing. So this slide is just to emphasize what we have just learned so that we can remind ourselves. We have said that this is a summary of what we have learned. Factors affecting illumination is assumption that the source is a point of source is, or in otherwise sufficiently far away the surface. So E is directly proportional to the luminous intensity of the source, and then inverse square law and the Lambert's law, you can see them there. We have already talked about them. So the inverse square law, we have said that we can see with the way we explained using this, that established by J. Lambert as one of the earliest lighting laws to enable the calculation of illuminance. So the illuminance of the surface is inversely proportional to the square of the distance of the surface from the source. So E is equals to I, and I, we say this flux, I r squared. Example is a luminous intensity. I don't know how to zoom out this so that you guys can see. Luminous intensity of a spotlight varies with angle. Its rate have a maximum value of 100 candles at a certain point at a beam. So if this light spotlight is aimed directly towards or onto the flat meter 2 meters below, what will be the luminance? So these are the calculations that can be calculated. The spotlight is angled at a luminous intensity directed to 100 candela. What will be the illuminance? So we said that from the formulas we can calculate those questions. So those are some of the questions that I would like you guys to attempt and discuss amongst yourselves. The Lambert's cosine law. According to this law, if the surface is turned so that the rays hit at angle, let me minimize because I cannot see it here. Sorry. If its surface is turned so that the rays hit at an angle, so the illuminated area will increase in a size and illuminance drop accordingly. So you can see there. So from the Lambert's square law, cosine law, the ratio of the original illumination area of the new area equal to the cosine angle through which the surface has been moved. So therefore, if the illuminance as will fall on a factor of the cosine angle. So it is E is equals to 1 over r squared cos A. An example is there, and you can calculate an activity, a lamp giving out 100 millimeters direction. I don't want us to do these calculations because there's a time when we are going to do the calculation. Illumination of multiple points. You can see how it is. So at point A, we have EB, that is the illumination at point B is EA cos cubed theta, and then we have at C, we'll have EA cos square theta, theta 2. And then at ED, we have that at theta 3. So those are multiple points. An example is there, and I've said these examples, we'll do them later when we shall have started the calculations. Now, activity of the corridor is there. Coefficient of utilization and utilization factor, that is the efficiency, and which is equal to the ratio of the lumen that actually received by a particular source of light and the total number of lumens by a high light source. So lumens activity received on the work plane, lumens emitted by a light source, coefficient of utilization or utilization factor, the type of lighting system, direct or indirect, type of mounting height of the fitting, color of the surface of the walls and ceiling, the shape and dimensions on the room. Those are the factors that affect the coefficient factor or the units of utilization. The example is there. You can try to do these examples, these calculations, and see what you'll get out of them. So that is the presentation today, and I will upload as a video, the last video, before we can now finish the laws of illumination. And I want you to keep preparing for questions. Prepare for questions and ask me about the topic we have done today. I'm uploading a video. Not that one. Now listen to this. I will give you this video. So let me hold it there. I've already loaded it into your portal. So guys, up to that point, I would like to hear questions from you. I would like to hear questions. I will not proceed with the video. Okay, so I would like to pause there and listen to what you have. Can I get questions now? Or any concern before we break? Salad? Salad, Peter, Kasheru,
Yes.
unmute your mic so that I've already finished my presentation. I want to hear what, any question, any problem, any comment. Yes? Nobody's talking.
Yes.
Kasheru?
Madam,
Yes.
what about these polar caps? Umesema tuachane nayo. That is not necessary ama?
Hizo haziko necessary kwa, you know, we have to take what is in your syllabus. So what you need to know is the laws of illumination, and the next topic we are going to start on calculations and how we can design. So whatever I don't discuss, it's not important in your syllabus. Okay?
Okay.
Swali lingine? Gasheru, hamna swali?